Good morning everyone. So myself Bhavan Kumar. So this is my third video of D block elements. So now we shall see after ionization energy we shall see the next property, that is oxidation state. One of the most frequently remarked characteristic of transition element is its great variety in oxidation state of their compounds. So whenever transition metal form compounds, the electrons present in 4s orbital as well as 3d orbital are involved in bond formation. Hence, these elements exhibit variable oxidation state depending upon number of electrons participating in the bonding. That means, so here as we said, the electrons which are participating in bond formation are 4s as well as 3d orbitals. So 4s it can have maximum of 2 electrons, and 3d subshell can have maximum of 10 electrons. So bond form, the number of the variable oxidation state as expressed by D block elements is because of 4s or subshell as well as 3d subshell. So you can see, so 3d subshell as it can fill maximum of 10 electrons, you can see variable oxidation state and maximum oxidation state. So you can see have more than one oxidation state for single element. So scandium, titanium, vanadium, so all will have more than one oxidation state. So that you can see here next. So here you can see variable oxidation state of D block, that is 3D elements. So scandium is having +2, +3, titanium +2, +3, +4, so on. When you come to manganese, you have +2, +3, +4, +6, +7. So iron is also having +2, +3, +4, even +6 is also possible. So here you have 10 elements of 3D block elements from scandium to manganese, that is first 5 elements. For first 5 elements it is found that minimum oxidation state is number of electrons present in 4s subshell, and maximum oxidation state is number of electrons present in 4s as well as 3d subshell. So from this you can understand what is the minimum oxidation state for scandium to manganese. From scandium to manganese, for first 5 elements, minimum oxidation state is number of electrons present in only 4s orbital or 4s subshell. So if it is as having almost all 4s subshell is completely filled, then remaining electrons goes on filling the 3d subshell. So minimum oxidation state is number of electrons in 4s subshell, and maximum oxidation state will be number of electrons present in 4s as well as 3d subs. For first scandium you can see +2, 4s is already filled, and +3. For titanium you have +2, +3, +4. Vanadium you have +2, +3, +4, +5 also you have. So for chromium it starts from +1, because as you see the atomic number is 24. So one electron from 4s orbital jumps to the 3d subshell to make it a half filled subshell, 3d subshell. So one electron will be remaining in 4s subshell. So it has, chromium also has +1 oxidation state, +1, +2, +3, +4, +5 and +6. It means, so you can see there are 6 oxidation states for chromium. So similarly, when you come to manganese, you have +2, +3, +4, +6 and +7. Here also you have 5 oxidation state for manganese. This is for first 5 elements. So when you come to the iron to zinc, from iron to zinc, minimum oxidation state is number of electrons present in the 4s subshell, but maximum oxidation state is sum of 4s electrons and unpaired electrons of the 3d subshell. So here you can see iron is having +2, +3, +4, +6. See cobalt is having +2 and +3, only 2 oxidation states. So because, so we have, as we said, it is number of unpaired electron. Cobalt is having completely filled 4s subshell, and 3d7 is for cobalt. 3d7 means you have 3 unpaired electrons. 3 unpaired electrons. So for nickel, so again you have completely filled 4s subshell, and 3d8. So we have only one unpaired electron. So like this, From iron to zinc, the minimum oxidation state is number of electrons present in 4s subshell, but maximum oxidation state is sum of 4s electrons and unpaired electrons of the 3d subshell. Thus, transition metals forms ionic compounds in their lower oxidation state, while they form covalent compounds in higher oxidation state. Higher oxidation state of transition metals are more stable down the group. Right, this is regarding oxidation state. As we say, all elements have variable oxidation state. Almost all elements having more than one oxidation state. From scandium to zinc, again I repeat, minimum oxidation state is number of electrons present in the 4s orbital, and maximum oxidation state is number of electrons present in 4s as well as 3d subshell. But from iron to zinc, the minimum oxidation state is similar to the first 5 elements, that is number of electrons present in 4s subshell, but here maximum oxidation state varies from first 5 elements. It is number of electrons present in the sum of number of electrons present in 4s subshell and unpaired electrons present in the 3d subshell. So this is about oxidation state of 3d block elements. So next we move on to the magnetic properties of 3d elements. So these properties, ionization energy, oxidation state, magnetic properties, color and complex, are very important properties with respect to the 3d subshell. So magnetic properties, so you have transition metals and their compounds exhibit magnetic properties due to partially filled d orbitals. It is due to the presence of partially filled electrons in the 3d subshell, that is d orbital. So we have, as we know, magnetic properties. There is two types of magnetic property. One is paramagnetic, another one is diamagnetic. A diamagnetic substance has all electrons paired up. Such a substance is repelled by magnetic field. So if you see paramagnetic property, paramagnetic substance contains one or more electrons. Such a substance is attracted by the magnetic field. So on this basis you can classify whether 3D subshell elements, 3D block elements exhibit paramagnetic or diamagnetic substance. Most of transition metals exhibit paramagnetic because they possess one or more unpaired electrons in their 3D subshell, and magnetic property is measured in terms of magnetic moment, and unit of magnetic moment is Bohr magneton. So here you can see how it is calculated. Magnetic moment of transition metals ions are calculated using formula mu is equal to square root of n into n plus 2, where mu is magnetic moment and n is number of unpaired electrons. So for example, if you take an example of copper ion, copper Cu plus 2 ion. For Cu plus 2 ion, the electronic configuration becomes 3D. Outer electronic configuration becomes 3D9 and 4s0 has one unpaired electron. Hence, magnetic moment of copper plus 2 ion is calculated as follows: mu is equal to root of 1 into 1 plus 2 is equal to root 3, that is equal to 1.73 Bohr magneton. Larger the number of unpaired electrons present in substance, larger is magnetic moment and greater is the paramagnetic character. So this is as the number present in larger is magnetic moment, larger is magnetic moment and greater is the paramagnetic character. So in case of here you can see iron, cobalt and nickel, paramagnetic behavior is highly pronounced. Hence they are called as ferromagnetic substance. Here you have more number of unpaired electrons. These are strongly attracted by the magnetic field. Iron is 1000 times more magnetic than ordinary metals. When iron is heated to 768 degree, it loses its ferromagnetic property, and this temperature we call it as Curie point. So this is one of the important definitions of ferromagnetic property, Curie point. If you have been asked what is Curie point, then when iron is heated to 768 degree, it loses its ferromagnetic property. This temperature we got as Curie point. So till now we have seen only paramagnetic and diamagnetic substance. Here one more property has been added, that is ferromagnetic, because when you come to the 3D block elements, you have three elements which are still more where matic property is more pronounced, that is in case of iron, cobalt and nickel. So these elements, especially these three elements, they are called as ferromatic substances because these are still strongly attracted by the matic field compared to other paramatic substances. So this is about oxidation state and matic property of 3D block elements. So in the next class we shall see about color of compounds and complex of 3D block elements.